Faculty of Social Sciences. I've taught multi-level modeling a lot, so I'm very happy for this class to, for you to interrupt me anytime you don't understand anything. And yeah, let's see how we go. We've got this workshop and also next week's workshop. So some of you hopefully will be attending both workshops. I hope you have all got the materials that were emailed out to you earlier on. That's the zip file, multi-level workshops 1 and 2 materials. So all of today's materials are in that zip file. Yeah. So if you haven't got the zip file, please let the course organizers know, and they'll be able to send you out. So everything that I'm talking about today is in the zip file, and we'll be going through that zip file as we go along. So for those of you who've got your computers, can you unzip the file? So remember, if you're on a PC, it's very important that you don't double-click the zip file. Double-clicking alone is not enough. You have to extract all the files. So you can either right-click and extract all, or if you've got other kinds of unzipping software in your computer, that's great. On Macs, it's slightly different. I'm not quite sure how to unzip, but you have to unzip all the files. So you get this folder, a new folder called Multi-Level Workshops 1 and 2. So once you have the unzipped folder, you just double-click on the unzipped folder, and then you have a whole series of files in there. So it looks very confusing, but let me go through all of those files so that you understand what it contains. It does contain a lot of data files. So all these TXT files are text files. It also contains a number of R script files. So you see this R 3.1, R 3.2. Those are R script files. So those are practical examples that are already scripted out for you. And on top of that, you have a few PDF files. So you have these PDFs over here. These PDFs are taken from a website called Lemma. So I'll tell you a bit more about the Lemma website. And also you've got the workshop slides from today and also next week. So workshop 1 and 2. So Lemma is the online learning course specializing in multi-level analysis. So it's been developed quite a few years ago now, but it's a really great online learning platform. It's free for anybody to register. So if you haven't registered already, here is the, I thought I had the Lemma website open. Okay, so you can just Google Lemma, LEMMA, multi-level, and the top hit should be this Lemma website, Learning Environment for Multi-Level Methods. It's from the University of Bristol, so it's bristol.ac.uk. You can just click on that. It does require you to register. So if you haven't registered, I think it's not instantaneous. So I think somebody has to verify that you're a person at an education department. So, but don't worry, I mean, it's completely free. So it might take a day or two for them to get back to you. Once you register, you can log in. So if you log in here, and with your username and password that you've registered with. Oh, I've forgotten my password. And it will take you to these the course. So on the left-hand side, you have a whole bunch of modules on doing learning statistics, learning data analysis. Initially, it's quite, it's not specific to software, and it's not specific to multi-level models, but from module 3 onwards, you have multiple regression. Modules 4, 5, 6, 7, 8 are all multi-level modules. So all of the files that I've taken, that I put in the zip file, from the data files to these explanatory PDFs to the practical files are all taken from the Lemma modules. Yeah, so if you want to learn more about multi-level models, you don't have to read this. You can go directly to the Lemma website where they explain things in much better detail than you would get from this just a few workshop classes with me. So that explains, why we've got so many files in the zip file that you have. It's all located in this Lemma website. So I really recommend that you register. It's free, and you learn more about multi-level models through this website because it's very well organized. It's very well detailed. Okay, so coming back to today. So today, what we're going to do. So I've given a little synopsis here of today's workshop. We'll be learning how to apply multi-level techniques to continuous normal response data, so continuous variables. And we'll be learning how to do this using R and understand why and when you should use multi-level models. So for those of you who are new to R, today will be a little bit hard because the R statistical software can be quite new and demanding. But again, the Lemma website takes you to how to learn R as well. So, and also those of you who attended the previous workshops on doing statistical analysis with R, you'll be quite familiar with R by now. So let me take you through the slides of today's workshop then. Okay, so as I said, we'll be learning about linear regression models, we'll do a quick refresher on multiple linear regressions, how to interpret coefficients, and how do you take account of categorical variables and interactions in your statistical models, and what assumptions you have in linear regression models. So as I said, you can register online for the Lemma modules free, and also please, we're running this in R, it's free, but you need to install it. So you do need to install the RStudio desktop, free to your computer. Now, those of you who are using Macs, sometimes the libraries that you use in RStudio are not compatible. So many times you have issues where you're running, I tell you, or somebody tells you, yes, use this command in R, and it doesn't work in a Mac. And so it's to do with different versions of Macs that are issued. Sometimes it's an older version of Mac that you're using, and it's not compatible with the commands. So for those of you who have those issues, especially with Macs, you can register for free on the POSIT website. POSIT is the software company that builds RStudio. So I'm just going to log out just to show you the POSIT cloud. You can use RStudio on the web. You don't even need to install it on your computer. Of course, there are limitations. It's free, but you can do quite a lot. You can do all of today's exercises on the web, for example. So you don't need to install RStudio on your computer. Either it's Mac or PC, you can just run it on the web. So you have to not subscribe, but you have to register, of course, but it's free to register. And this one is instantaneous. You can register instantaneously. Once you register with your user ID, you just need to log on. And what's my password? Okay, and once you log on, you say, okay, it asks you what to define a workspace. So it looks a little bit weird, what is a workspace? But the workspace is your RStudio thing. So you just have to click on, your workspace. Click on a new space. You can call it test or call it whatever. click on that. Oh, no, that's not. I actually forgotten how to do this. Well, it's you can click on an untitled project. Oh, it's a new project. Click on new project. Yes, that's the one. And posit what you wanted to, whether it's an RStudio project or Jupyter Notebooks project. So we're working in RStudio. Just click on new RStudio project, and it'll take a little bit of time to actually load it up. But once it's loaded up, you'll have exactly the same screen, RStudio screen on the website as you do on your computer. Yeah, so you can work with RStudio on the web, completely free of charge. The only slight, not even slight hiccup is that you have to upload your data set to the internet. So here's this upload button here. So you can just, whatever text or data file, you can just click on upload here and upload the data file to RStudio on the web, and you can work with that. As I said, of course, there are limitations on stuff that you can do, but all of today's exercises can be done on the web as well. So just coming back to today. Okay, so let's have a little test. Okay, you're not going to get scored, but just a little refresher of what linear regressions are. So hopefully you're all familiar with this type of equation where we're trying to model a dependent variable and outcome, y, as a function of some explanatory variable x. Yeah, and so the relationship in a linear regression model is one that's defined by your outcome is equal to the intercept, the alpha term here, plus the slope of x, plus some error, yeah, the residuals. So all of these terms mean, so A or alpha is the intercept, which is the value of y when x is equal to 0. Beta is the slope, and the interpretation of beta is the change in y when you go from 0 to 1 in x for 1 unit change in x. So that's the standard linear regression model. So let's have a little test here. Here's a scatter plot of age and systolic blood pressure. This is in 33 women. Yeah, so their blood pressures of 33 women. Here's a scatter plot. So what's the correlation coefficient in this scatter plot? Is it A plus 0.12, B minus 0.22, C plus 0.07, D minus 0.85, or E 0? For those of you who know the answer, it will be quite obvious. Hopefully the answer is quite obvious to all of you. So how many going for E? Anybody going for D? C? B? Or A? A lot going for A. Okay, so A is wrong. Can anybody tell me? Can anybody tell me why A is wrong? Yes, that's right. Correlation coefficient is always bounded between -1 to +1. Yeah. So I think some of you were thinking +1.2 because you're thinking of the beta coefficient. Yeah. So the beta coefficient, yes, that can go to unstandardized beta coefficient can be above 1, but we're talking about the correlation here. So correlation is always between -1 to +1, and a correlation of 0 is would be there's no relationship. Yeah. So of course it's positive, it's going up. If it's going down, if the scatter plot is going down, then it'll be a negative correlation. So a little bit tricky test there. But these kinds of figures hopefully are very familiar to you, where the slope is the line of best fit. So this best fitting line is defined by minimizing the residuals, the sum of the squared distances between each individual point and the line of best fit. Yeah. So visually, what we're trying to do with a linear regression model is to fit a best fitting line that minimizes the sum of the squared residuals. And remember, the residual is the distance between the individual data point and the best fitting line. And so once we have the slope, we can calculate, once we have the line of best fit, we can calculate the slope, which is the change in y for a 1 unit increase in x. Yeah, so that's the formal definition of slope. And then the alpha or intercept parameter is what is the value of y when x is equal to 0. So that's the intercept over here. So these are the terms in a linear regression model. The E there, the residuals. Today's workshop will be very heavy on residuals. So we'll be looking at ways to understand the residuals and decomposing those residuals. So the residuals, the error terms, the error is just all of these residuals. You add up all of these residuals together. That will give us the error term. And of course, we want to minimize the error. We don't want to have a very large error. If you have very large error, that means our model is not very good. Our line of best fit isn't a good fitting line at all. So this is some typical examples from a linear regression model output. We're modeling blood pressure. So blood pressure is the y variable over here. We've got 2 explanatory variables, age and sex, and an interaction between age and sex. Yeah, so age multiplied by sex. So here, let's have a quick, it's not a tricky one, but what is alpha and beta here? Yeah, what is the alpha here? The intercept. Yeah, the constant. Yeah, the constant. I heard the constant. So the alpha is 100.683, which is the value of systolic blood pressure when age is equal to 0 and sex is equal to 0. Yeah, so I don't know whether age has been centered over here, but if age is equal to 0, that doesn't quite make sense. So usually we would center age around the mean. So when mean age is 0, so that when you have the mean age, you have a systolic blood pressure of 100. And sex, I think sex equals 1 is man. Yeah, so sex equals 0 is women. So this is the systolic blood pressure of a woman of potentially average age. And then if you're a man, you add 17.279 plus however old the man is. Yeah, so if the man is of average mean age, then we don't have to worry about the interaction term. But if the man is, say, 1 year older than the average mean age, then the estimated effect, so the predicted blood pressure for a man, sex equals 1, who is 1 year older than the average, so it's plus 0.717. So we're adding all of that to the constant plus negative 2.74. So it becomes a little bit complicated. But yeah, so this is basically saying men have got more higher systolic blood pressure than women. They have on average 17.279. I think it's mmHg blood pressure higher than women. And if you get older, your blood pressure increases. So for every 1 year increase in age, your blood pressure increases by 0.72. But the sex difference, so the difference between men and women reduces as age increases. So that's the interpretation of this interaction term over here. So this goes through the various calculations, but I'm sure you can work it all out. And the other thing that I think you're all familiar with are the testing the model assumptions in a linear regression model. So normally, one of the key assumptions is our error terms are normally distributed. So the residuals are normally distributed. So remember, as I said, we're going residual heavy in today's workshop. So these are the residuals. So each of these residuals comes from an underlying normal distribution. So that's one of the key assumptions. And we test that using a QQ plot, a probability plot like this. So we're seeing for any significant departures away from this linear line. So if you have very excessive curvature, then it means here the residuals are not normally distributed. So so here's another way of visualizing this. So the residuals are meant to be like this, distributed at each point of x. Yeah, so they're all normally distributed. They're not meant to be skewed this way and skewed this way. So that would mean that this is not the line of best fit. So the residuals have to be normally distributed. The second assumption there is that the variance of the residuals is constant. So you can see here that the normal distribution of the underlying residuals is the same. Yeah, it isn't increasing or decreasing. So here you can have a normal distribution here and a normal distribution here, but very often what you get is a normal distribution that is much larger, a much larger distribution than a normal distribution here. So the variance in the residuals is increasing as x increases, or the other way around. The variance in the residuals can be decreasing as x increases. So you've got this situation of heteroscedasticity, which is a problem for linear regression models. So this is the standard way of denoting those top two assumptions, that the error terms, the residuals, are normally distributed, so capital N, with a mean of 0 and a constant variance. So constant variance is that sigma squared. So that's the typical statistical notation that people use to denote those top two assumptions. The third assumption is that the residuals are uncorrelated. It's to do with that there isn't some other third factor, a confounding factor that is affecting the distribution of the residuals. So it's more like a causal assumption. But the distributional aspects of the residuals, that's what's shown in those top two assumptions. So multi-level models is really about being able to relax the second assumption that the variance of the residuals is constant, because it allows for heteroscedasticity. So I'll come on to that. So I'm just doing the refresher of linear regressions right now. So the other thing is statistical significance. So we often test for whether a coefficient is statistically significant by dividing the coefficient by the standard error of the coefficient. So if that coefficient is, sorry, if that t-test, this is the t-test, if that t-value is large, if it's greater than 1.96, then it's statistically significant at the 5% level. So often we're looking for large values of the t-test in order to see whether the coefficient is statistically significant, and then we can construct 95% confidence intervals around that coefficient. The other thing is quite useful to get a measure of model fit. So depending on what kind of model we're fitting, we can calculate the deviance. So it's an overall model fit, or an R squared is the other one. So the deviance is a measure of goodness of fit of the model, and we're trying to reduce the deviance whenever we compare two nested models, two models that are elaborations of each other. We're trying to sort of reduce the deviance. The deviance is -2 times the log likelihood. So it's a measure of goodness of fit. And so often what we do is we do things sequentially. So you add in an extra parameter to the model, whether it's an explanatory variable, and then you compare the model with and without that extra parameter to see which one has the better fit, and whether there's a significant improvement in the fit of the model when you add in more explanatory variables. Yeah. So hopefully that should be quite familiar to you from linear regression models. We'll be working a lot with this particular data set in today's workshop. So it comes from a Scottish students doing exams, and Scottish students doing exams in different periods from 1984, 86, 88, 1996, and 98. So these are different cohorts of students doing a standardized test. So the Y variable, we're trying to explain what influences their exam test scores, which range from 0 to 75. We've got the ID, the anonymized ID of the student. We've got their sex, so 1 is equal to female, so 0 is a male student. And there are measures of social class as well. So 1 is managerial, 2 intermediate, 3 working class, and 4 unclassified. So the social class of the, I think, fathers. And there are about 34,000 students in this data set. So let's open up R, yeah, and see how it goes. So in the red, it says, for those of you who have downloaded RStudio, just double click on the file 3.1. So remember, you've got to open it up from the unzipped folder. If you double click on, if you haven't unzipped it, it won't work. So double click 3.1 from the unzipped folder, and it should automatically load up RStudio here. So this is a quick reminder about the RStudio interface. It's very much a programming-led analysis. So all of this, as I said, all of these scripts come from the Lemma website. Let's first of all read in the data to R. So the data, it comes from the text file 3.1.txt. So all we have to do is highlight that line 24, double click it or highlight it and run. And in the environment tab, hopefully you have the data set loaded over there. Yep. So if you want to see what the data set looks like, you can click on My Data, and it will open up what the data set looks like. So you've got the student ID, the exam test scores, which cohort they belong to, whether it was the 1984, 86. So 1984 is -6, and I think 1990 was 0, as well as whether they're male or female student and what social class. So hopefully you've all managed to open the data set. Let me see what instructions are next. Okay, it's about the user directory. So here it can be a little bit tricky for those of you unfamiliar with R. This time the data set is located in the same folder as 3.1.r. So it understands it very easily. Otherwise, you have to put in the folder location of where the data file is. And if you're anything like me, R is particularly annoying because the folders, it doesn't accept forward slashes, it only accepts backward slashes. So when you copy and paste the folder location, for example, from your PC folder location to R, it won't accept it. You have to redo it, get all the backward slashes in. It's very, very annoying. I don't know, and I don't even know how it works in a Mac situation. So it's always great, it's always useful is if your RScript file is in the same location as your data file. You can change your working directory to where your data file is. So in the session, you can set your working directory to wherever your data file is. So that is, you can choose what directory it is and so on. So that's really easy. But the other way you can also import the data file directly. So you can click on import data set, and it will and then you can tell R where that data file is located. So there are various ways of reading the data into R, and yeah. So this is yeah. So now we've imported this relatively small data file with very few variables in it. First of all, we always want to check what our variables look like. So extremely important to do that before doing any analysis, especially with our dependent variable. We always need to check the distributions. So here we look at the histogram of that. So we can this is the histogram command in R, hist, or short for histogram. So remember, in R, you've always got to tell R where the variable, which data set the variable belongs to. So in the read file over there, my data, we've told R that we've defined a my data file. So my data $score refers to, sorry, my data $score refers to the variable score in the my data file. Yeah. So again, if you're unfamiliar with R, it can be quite annoying because you often say, okay, you type in your variable name and R will say, oh, what is that variable name? I don't recognize it. So you always have to tell R that you're referring to a particular data set, a particular variable within a particular data set. So the my data refers to the data name, and after the $sign refers to the specific variable. And with the limits of the x-axis going from 0 to 80. So this will give us the histogram over here, if you double click on that. So first of all, you'll see that it's not a continuous distribution. It's not a normal distribution because unfortunately a lot of students get 0. Yeah. And then even with the rest of the scores, it's not a normal distribution because very few students score in the above 60. Yeah, most of the students are very much skewed this way. So it's not a great dependent variable to analyze because it's not normally distributed, but still you can run a regression model on it and check to see whether the regression model assumption of that the residuals are normally distributed hold. So that's another thing for those of you who are saying, oh my God, my dependent variable is not normally distributed. I cannot run a linear regression model because we assume that the residuals have to be normally distributed. So that's completely untrue. Yeah, you can have a very non-normal distribution of your y variable, of your dependent variable, and still get residuals that are normally distributed. Yeah. So the fact that your dependent variable is not normally distributed is not a bar, so that's a double negative. Just because your dependent variable is not normally distributed, that doesn't mean you should not run a linear regression model. It's perfectly okay to run a linear regression model because even though the dependent variable is not normally distributed, the key thing is that your residuals have to be normally distributed, and they can be normally distributed even with this kind of distribution. So that was the histogram. And then the other thing, apart from checking the distribution of the independent variables, we also want to see what is the association between, say, cohort 90 and score. Yeah, so this is telling R to plot a scatter plot between cohort 90 and score. And you will get this not very useful scatter plot. It's just and the reason why it's not very useful is because cohort 90 is not it's not a very continuously distributed variable. So there's very few values of cohort 90. So it's really hard to tell whether, whether there's a relationship between cohort 90, as the student cohorts get younger, is there an improvement in their exam test scores? It's hard to tell from this kind of scatter plot. So for those of you who want to know how to do that, you can use this plot command over here. So that plot command will give you the scatter plot over here, which is not very useful. So what might be more useful is to construct a table that is that looks at the mean values of the scores by different values of the cohort 90. So this is the mean exam test scores, the standard deviation of those means, the number of students in each of those cohorts, and this is which cohort they belong to. So if we construct this kind of table, we can see very clearly that there is a pattern here. So as the cohorts become younger, so this is 1984, I think, 86, 88, 90, 92, 94, you can see that the exam test scores increase quite a bit. Yeah, so from 23.6 to 41. So for those of you from the School of Education or Faculty of Education, you think, oh, great inflation. This is exams getting easier, maybe, or are the students getting smarter? We can run a linear regression model to see which of these factors are important. So to construct this table in R, it's slightly cumbersome. I'm sure there are better ways of doing it now, but this is the commands are all over here from line 44. From line 44 to line 52. So you all have to highlight these here because you have to keep telling R every time you want to create a new variable, you have to keep telling R what that new variable is and what you want, how you want to configure that new variable. And here is the result of that over here. Okay, and you can do correlations as well. So in the final bit of this refresher, we're just going to fit a linear regression model. So in R, the linear regression command, we have to tell R what do we want to call the results of this linear regression model. So this we can call whatever, we can name this model whatever we want. But the important thing is LM is linear model. Yeah, so this is the linear regression model command. Our dependent variable goes here. And this squiggle or tilde, after that are all our explanatory variables. So here we've got cohort 90, and we're telling R that the data set comes from my data. So it's a relatively simple command, so we can fit that in R. So we can fit it. R runs it, but not very usefully, R doesn't tell us what the results of that linear regression model are. So to find out what those results are, we have to ask R to provide a summary. So the summary of fit that linear regression model. So here it's telling us what the intercept is, 30.78, what the beat up slope is. So for every 1 unit increase in cohort 90, the exam test score increases by 1.32. So remember, cohort 90 is centered at 0. So at when it was a 1990 cohort. So you would think that this should refer to the test score when it was cohort 90 equals 0. Yeah, so 30.78. So hold on to that intercept score, 30.78. It should be what the mean we got over here. So when cohort 90 equals 0, yeah, our cohort our exam test score was not 30.78, it was 29.10. Yeah, so is this a problem? Why are we getting different results? I mean, the intercept is the value of x, sorry, the value of y when x is equal to 0. Yeah, so when x is equal to 0, y should be 29.10, and yet in our linear regression model, our intercept is a little bit higher than that. It's not far away, but it's about 30.78. Can anybody tell me why? There is residual, yes. But it still should be able to estimate what the correct mean of what is the value of y, our score, when x is equal to 0. So the residuals by alone won't explain it. The trick here, the trick question was that here I've modeled cohort 90 as a continuous variable. Yeah. So what cohort 90 is not a continuous variable, it is a categorical variable. It goes from minus something, minus 6 to plus 4. Yeah. So if we had modeled cohort 90 as a categorical variable, if we told R that actually cohort 90 is a categorical variable, then you would get the correct answer. So the next question you might ask me is, how do we do that? And I've completely forgotten. So that's the thing about R. For those of you, if you're like me, who I only use R occasionally, I often forget what are the commands in R. So again, thank goodness for ChatGPT, because before ChatGPT, finding out commands in R was a bit, I don't know, you Google it and sometimes you get all kinds of conflicting answers. So with ChatGPT, in particular, Poe is the specialist ChatGPT language for statistical software, for programming, basically. So you can create your own. It's free to use, and you can ask it all kinds of questions around language. So I've gone into Poe, and so I'll ask, how do I declare a categorical variable for analysis in R? Okay, so we have to declare the variable as a factor. So we have to, it's almost like generate a new variable that is called a factor of that particular data set. So variable. So let's just copy that across into R. Where should I put it? So I'm just going to call it categorical score. And okay, what happens if I just say factor score? So I copy pasted the command, the example from Poe. Let's see what R will say if I try to run this, and it will complain. It'll say, "Wow, score not found," and that's because I forgot to tell it that score is located in my data. Yeah. So remember always to put in the my data part of score, so my data $score. and run it. So now it's generated a new variable called, which is a categorical version of score. And now if we try and fit that model, so instead of using cohort 90 as our explanatory variable, let's use categorical, oh no, apologies, I used the wrong explanatory variable. It should have been cohort 90. So here is the thing. Categorical should be cohort 90. Factor cohort 90. So we want to generate a categorical variable of cohort 90. Yeah, so, and then replace our linear regression model explanatory variable with that. So instead of cohort 90, I'm replacing the explanatory variable by categorical cohort 90. So if we run this linear regression model and see the fit data, you can see that it's generated the different values of score, exam test score for the different levels of cohort 90. And our intercept is now, it's not 30 points. That's because we haven't set the correct reference term for this. So it's got -4, -2, 0, 6, 8. So it's, I think, yeah, I think it's used -6 as the reference term. So -6 is when cohort 90 was the cohort was in 1984. So it's 23.666554 is the score then. And if we look back at the table, hopefully, yeah. So -6. So that was the exam test score of the cohort 90. So that's a very long-winded way of telling you, reminding you about linear regression models and some basics in R. And again, just about getting a little bit familiar with R and using Ho to help us along. So the other bits of the slides that do the refresher on linear regression models is just to fit the QQ plot, the residuals, and so on, and you can just follow that through yourself. So here we're checking for heteroscedasticity, so the variance of the residuals, whether they're increasing or decreasing as X increases. Here, there's not much sign of that. It's pretty much the same variance that we observe in the residuals as X increases or decreases. So not much evidence of heteroscedasticity. And then we can check to see whether the residuals are normally distributed using this command in R. Okay, so let's go on to multi-level data structures. Yeah. So why should we use a multi-level model? So the main thing is very often in the real world, the assumptions of homoscedasticity and that our residuals are independent of each other, that tends to be violated. And very often our data comes in a hierarchical structure. So if you're working in education in schools, for example, and we're very interested in seeing what affects students' scores, but students are clustered within classes. So very often, each individual student is not a separate data point, but somehow we're sort of ignoring the influence of classes if we're treating each individual student as a separate data point. And you can think about other hierarchies as well. So each class is nested within a school, and different schools. You can imagine schools have an effect on individual student pupil outcomes. So treating pupil scores as though they're independent of their classroom effects as well as they're independent of school effects is not meaningful. The other thing, here's another example, individuals within households. So clearly, you can think again here, individuals within households, within communities, neighborhoods. So all of these higher levels like households and communities, neighborhoods can affect individuals as well. And here's another typical example. Here, the level one is not the lowest level. Level one is not an individual. It's the repeated measure. So the level two is the individual. So level one is the number of occasions students take a particular test. So again, how students do in exam is very much affected how they did in the previous exam. So to take account of this kind of clustering in the data, you can run a multi-level model. So what is the level? And this, I think, is the most philosophical part of today's class. And this is the one where I think a lot of people kind of make mistakes. So remember, a level is something that is a random variable. So it has to have a random classification. So always we're thinking of units that can be generated from a random sample of a wider population. So for example, here, if we are thinking about students nested within classes, then we're usually taking a random sample of students, maybe 5, maybe 10 students from a random sample of classes. Not all the classes in the school, maybe 5 or 10 classes within the school. So think of it as the reason why we're doing a multi-level model is because we want to generalize to the wider population of students or the wider population of classes. If there are only a fixed number of categories, then that's not a random variable. Yeah. So we think about sex, for example. Say if there's just 2 sexes, male, female, there's no wider category of sex that we wish to generate to. So we wouldn't have sex as a level in a multi-level model. So that's the easy one. Then the ones where I've seen people use multi-level models a lot is in, say, country. In different surveys in different countries, they say they've done a survey of 1,000 people in 10 European countries. And it's true, yeah, there are more than 10 European countries. You want to generalize to the wider sample of countries within Europe. So it kind of makes sense. Sometimes they have all the European countries. Say there are 30 European countries in total. So they have all the surveys done in 30 European countries. There is no wider sample of European countries to generalize to, but they still run a multi-level model. And there it gets a bit philosophical. So they say that you can generalize to not another European country because there isn't, but the same European country, but a survey conducted in a slightly different time. Yeah, say the survey was done 1 month earlier or 1 month later. So you can think of it because the survey is just a snapshot in a point of time. And so maybe you want to generalize to all the potential surveys that could have been done around, plus or minus 1 month from the time of the survey in a country. So that's the way how people get around with generalizing to a wider sample when you've got a fixed classification. So in general, if you have a variable that has fixed categories, so say sex is relatively easy, there's just two categories. But say it's ethnicity, yeah. So ethnicity has many categories, can be 5, can be 10, yeah. Sometimes even more. But usually, where we wouldn't use ethnicity as a level in a multi-level model because it doesn't make sense to generalize to a wider sample, of ethnic categories, ethnic or racial categories. We don't know what that means. Yeah. So think of it as in terms of measurement issues. So when we've got a fixed variable is when we can measure things quite well. Yeah. So sex, you can measure quite well. Maybe self-reported ethnicity, you can measure quite well. So those kind of things. So if we're interested in schools, so the type of school, whether it's a private or public school, there are only, maybe there are sort of more than 2 types of schools, public, private, then some sort of combination, or religious schools. Maybe there are 4 or 5 different school types, but you can measure that pretty well. There is no additional sample of school types that you want to generalize to. So school type wouldn't be a random variable. It wouldn't be a variable to which you want to generalize to a wider sample. So this is a very long but very important point, because very often I see a lot of analysis done where of multi-level analysis done where the level, the second level in particular, doesn't seem like a correct random variable. So it often seems like it's really a fixed characteristic, and there I think, yeah, we have to be a little bit careful when doing multi-level analysis. So here's some variables: citizen ID, what they intended to vote, which area they live in, their age, their gender, and ethnicity. So which of these variables can be treated as a random classification in a multi-level model? Citizen ID. Can you think of, yeah, is this a random sample that we want to generalize? If we didn't have this ID, citizen ID, we had another citizen ID that we want to generalize to. Does that make sense? Yeah. So the answer is yes. We do want to generalize to a wider population of citizens. So you can think, yeah, okay, if it's not this particular citizen ID, then we want to generalize our analysis to a wider population, to a different citizen ID. So yes, we would treat citizen ID as a random variable, as a potential multi-level variable. Voting intention. So this comes from the UK government politics. So in the UK parliamentary elections, there are very few parliamentary parties. Very few there. I mean, having said that, actually there are very few large parliamentary parties. They're like 3 or 4 main parties. There are a host of smaller parties. Say there are 20 parties in the UK system, and you collect people's voting preference. Even for the smallest party in the UK system, you can ask people whether they want to vote for the smallest party. Would you treat the voting intention as a random variable for multi-level analysis? Yes, I'm getting a few shakes of the head, so no. So even though you've got like 20 categories, you say, oh yeah, what does it mean? I want to generalize to a wider sample of voting intentions. It doesn't make sense. So you wouldn't treat this as a variable. Area, so area, very much so. You want to generalize to a wider group of areas, that's fine. Age, this is interesting. So here we've got age 64. And obviously, we want to generalize to people who are not 64. Yeah. But does it make sense to treat it as a random variable? So it doesn't make sense because there is, you can age is perfectly measured. It can be perfectly measured. So of course, people can lie about their age. They can misremember their age. They can make all sorts of mistakes. But really, it's an issue about measurement error. Yeah. So where we've got a variable that can be perfectly measured, like age, like voting intention, then it doesn't make sense to generalize to a wider population. Yeah. So we can we wouldn't treat age as a random variable because it can be perfectly measured. If it's perfectly measured, then there's no point generalizing to a wider sample. So gender, of course, we talked about age, sex before, and ethnicity as well. So we wouldn't treat either of these as a random variable. So here's a test. So supposing we're interested in looking at the differences between boys and girls, educational achievement, and how that varies across their secondary schools, and they're 16 years old. So which of these sampling designs do you think is appropriate? Remember, we're interested in the difference between girls and boys in different schools. Yeah. So what if we sample 5 schools and take the achievement scores for 100 boys and 100 girls in each school? So just 5 schools, but a lot of boys and girls. Or a few more schools, you sample 30 schools, but take just 10 boys and 10 girls. Or C, we sample a lot of schools, but just 1 boy and girl from each school. So which one of these sampling designs is most appropriate for the question? Anybody going for C? Anybody going for B? And anybody going for A? Yeah, the answer, yes, definitely is B. Of course, it's partly because it's in the middle. So this is really extreme, and this is also quite extreme. But also, remember, we want to have an adequate sample size of both schools and boys and girls, because we want to generalize to a wider sample of schools, because we think that the difference between boys and girls varies between schools. So we need to have enough schools. Here we just have 5 schools in A. It's not enough. Here we have 30. Ideally, we have more, but we have 30 schools, so maybe it's enough. Here we have a lot of schools, but just 1 boy and girl from each school. So how do we know that the difference between boys and girls is really significant or not when we just have a sample of 2 from each school? Yeah, so the sample size at level 1, which is at the individual level, is too small here. And here the sample size at level 2, which is at the school level, is too small as well. So multi-level data structures are, they can be generated either from the way how we collect the data, and very often we collect survey data from using a clustered sample design, or there are natural structures within the population. So, we won't go into that, but it doesn't really matter. But the natural structures within populations, so that's why people look at country as a level, because they're interested in country differences in people's attitudes to various things. So let's go on to why we use clustered data. Why do we use multi-level analysis? It's because if we don't use it, then our standard errors are too small. So the standard regression analysis, if we ignore the clustering in our data, if we ignore the fact that there's grouping in our data, it means that we're treating each observation as an independent data point. And really, that's not valid. Because we're ignoring the fact that the students within a class or within a school are more alike than students from other classes or other schools. So what might look like statistically significant results because your t-test is significant, because your standard error is a lot smaller than it should be, is really problematic. So we need to take account of clustering. So that's the technical reason why we would do a multi-level model, but often we're interested in actually, if you're like a sociologist like me, we're interested in group differences. We're not really interested in individual differences, but we're interested in why groups differ. Why does one class perform better than another class? Is it because of the school teacher, or is it because of some other factor? Is it because you have a very disruptive student in one class, or a very good set of students in another class? So these kinds of classroom level factors, this higher level factors, we're looking to use these as explanatory variables in order to do this kind of analysis where we're looking to understand differences between individuals in terms of higher level factors, in terms of classroom, country, neighborhood level factors. We have to run multi-level models. So very often our substantive research question of interest is not at the individual level, it's at the higher level. So just some notation. So I refers to the level 1 unit, so individual. J often refers to the higher level unit, so either the area or school level. So X, which is our explanatory variable, or Y, our dependent variable, can have an ij subscript. So the Y, the outcome variable, the dependent variable, has an ij subscript, meaning it's for individual I within group J. And we're saying this Yij is a function of X variables that can also be Xij, or some contextual variables. So here, these are group level characteristics that are the same for all the people within J categories. So they don't have an ij subscript, they just have a J subscript. So we're interested in these group level characteristics, how this affects. So here is an example of life expectancy differences in London MTR stops. So here we've got very high life expectancy, 78.5. Here we've got low life expectancy, relatively low life expectancy, 73.6. So if you're interested in understanding why is it that life expectancy here is much higher compared to here, just 5 or 6 MTR stops away, we have to look at not just the characteristics of the conditions in these tube stops, but also the characteristics of the individuals living in these different MTR places. So we have to run a multi-level analysis. We can not run the multi-level analysis. Then what happens? What are the other ways? We can ignore the problem, but then that's a problem for our standard errors. So we'll get incorrect results, and we can make inappropriate inferences about statistical significance. We can run standard models with robust standard errors. So these robust standard errors will take into account the clustering in our data. So that's entirely fine if you're interested in making inference, if you're not interested in making inference at the level 2. So, but if you're a person like me that's interested in the effect of the context of the group, then this won't help. We need to run multi-level models, or option C, we can run fixed effect models. So fixed effect models are one in which we sort of control for group membership as a dummy variable. And I didn't talk about aggregate analysis as well. So we can, instead of analyzing things at the individual level, we can just analyze things at level 2, at the group level. So we can calculate a mean of Y and a mean of X at the group level and correlate that. But, those of you who know about ecological fallacy, just because there's an association at the group level, that doesn't mean you will find the same association at the individual level. So the aggregate level analysis is not useful. The disaggregated level analysis, ignoring the problem, is not good. Robust standard errors means you're not interested at group level effects. The fixed effects model is also possible, so we can get, we can control for a set of dummy variables that is basically each group type, yeah? So each type of level 2 group. So, it makes sense maybe if you've got very few group types. So say, in the example of 10 European countries, yeah, got a survey data set of 10 European countries, then yeah, okay, then you don't really need to run a multi-level model. We can just include the country as a group variable. Yeah, so you've taken away the influence of the context, and then you're seeing what happens to your individual level associations. So that is possible, but still, you know, if you've got like 100 groups, say 100 schools in your data set or 100 classes in your data set, then it becomes, you know, very messy, because then you're putting in a dummy variable for 99 other classes or 99 other schools. Then it becomes a very complex model. So really, the fixed effects model is usually not that useful. And so we would run a multi-level type model. And here the multi-level model, you know, two things to notice here. So the ij subscript, yeah, so individual I within group J is equal to the intercept. You all understand what intercept here is. The error term. So the error term, this error term, Eij, has an ij subscript. So it's the error term for individual I within group J. What is new is this uj subscript. So this variance, this error term at the group level. So the multi-level model decomposes the overall error in a linear regression model into two parts: a group level error and an individual level error around the group mean. So I have talked nonstop for over an hour. Can we take a 5-minute break and then we'll come back, okay? I'll be here for those of you who want to ask any questions. Okay, so let's start again. So if you remember, we were looking at this very basic multi-level model equation. Yeah, so there are no explanatory terms in it. All we've done here is to decompose the overall variance, the overall error term, into two components: the group level residuals and the individual level residuals. Yeah, UJs and the EIJs. Looks simple, but it comes with a whole bunch of assumptions. Remember, each linear regression model has a whole bunch of assumptions. Multi-level models have even more assumptions. So the UJs refer to the group level residual, group level variance. The EIJ refers to the individual level residuals or individual level variance. Remember, each of these have assumptions, so they have to be each residual has to be normally distributed with a mean of 0 and a constant variance. Yeah, so UJ and the EIJ, both of these have to be normally distributed with a mean of 0 constant variance. The same assumptions, but now two residuals have to be like that. In addition, the other standard assumptions is that there's no correlation between the residuals, either at the group level or at the individual level. Yeah, so the covariance between UJ and UL, it should be 0. There's no correlation between each type of group residual or each type of individual residual. And there should be no correlation between the individual level residuals and the group level residuals. Yeah, so the covariance between EIJ and UJ should be 0. So there is a cost to multi-level models. The cost is these assumptions. And it's not just one or two assumptions, it's a whole bunch of assumptions, you know, at each group and individual level, as well as the covariance between the group and individual level residuals. This is why a lot of economists hate multi-level models. They're saying, you know, how realistic is it to assume all of these things? Economists, they prefer to make things not so complicated, you know, and they want to make the models more meaningful. Yeah, so fewer assumptions is better, and that's completely true. But for other people that are interested in group level effects, it comes at a price of all of these assumptions that we need to make. So the standard thing is economists, they like fixed effects models, and sociologists like multi-level models. But of course, it's not a disciplinary divide, but it's really a divide about what is the underlying research question. So, the next part is we are going to understand a little bit more about this very basic multi-level model. It's called a variance components model. So it decomposes the overall variance into two parts, the group and the individual level model. So, just a reminder, the simplest possible linear regression model is yi equals beta naught plus some error term. No explanatory variable in that. So beta naught is just the mean of y, and ei is the residual for y for the ith individual, and we assume that these residuals are normally distributed with a mean of 0 and constant variance. So this is how we would visualize this. So if there's a y-axis over here, beta naught refers to the mean of y, and these are the individual data points, and how this is the distance between the mean line and the mean of y and each data point. And so if we add all of these residuals up, we would get our EIs. So that is the visual representation of the basic linear regression model without any explanatory terms. And the basic multi-level model is almost identical, except we now have the ij subscripts and we have the uj term. So this uj term changes the meaning of the ei subscript. So this eij subscript is now changed, and visually this is how we represent this. So this beta naught line is still the average for y in the entire data set. But now we have, say we've got two groups here, U1 and U2. So U1 refers to these gray rectangles, and U2 refers to the data points denoted by these black dots. So the gray rectangle, the mean of the gray rectangles is this dotted line over here. And U1 is the distance from beta naught to the mean of this group. The mean of the black dots is denoted by this line over here. So U2 refers to the residual from the overall mean to the group mean. So U1 and U2 refers to the group level residuals. So that's UJ. And EIJ refers to the individual level residuals from the group mean. So it's the difference between this data point to the overall group mean, or this data point to the overall group mean. So if we add both of these residuals up, the residual from the individual level residual to the group mean, and add all of those residuals up plus the group level residual, we would get EI. You would get all the overall residuals. So that's what the multi-level model does. Basically, it sort of decomposes the overall residual into the group level residual plus the individual level residual around the group mean. So that's all the multi-level model is. So it's saying, okay, we're estimating this group level residual and the individual level residual around the group mean. So here's some examples of a weight as our y variable. We've got people living in different places in England, and here we've got people living in Hayes that are a bit heavier than average, people living in Kew who are a bit lighter than average, and people living in Purley who are close to the average. So for each of these data points, we can calculate the UJs, the difference between the mean of Q to the overall group mean, or the mean of Hayes to the overall mean, as well as the EIJs, yeah, the difference between each individual data point to their group mean. So remember that visually, because that's the key to understanding multi-level models. So we can, here's one example of the clustering of weight in different areas in London, Hayes, Kew, and Purley. And here's another example. Yeah. So in these two examples, which one do you think is one where the influence of place matters more for weight? So we're interested in whether place has an effect on people's weight. And we have these two kinds of figures, figure A and figure B. So which one of these figures do you think is one where place has a greater influence on weight? Is it this one? Anybody going for this one? Or is it this one? Yeah, a few, yeah. So visually you can see, yeah, it is this one, because there's much smaller clustering around the group mean compared to this one. This one, there's much greater the much greater variability around the group mean. So here the group mean doesn't matter so much, yeah, for people's weight, but here the group mean matters a lot more. To once you know the group mean, you pretty much understand much of the variability in weight. So this is an illustration of how you can use multi-level models. So the partitioning of the variance, as I said, we assume that the group level residuals and the individual level residuals around the group mean have all of these assumptions. What we can do is to calculate the variance partition coefficient. So the VPC is just the UJ divided by UJ plus EIJ. So apologies for different notations, but sigma squared U is the group level residual, group level variance, and this is the group level variance plus the individual level variance. So if you add up all of the UJs, you get the sigma squares U, the group level variance. And you add up all of the EIJs, you get the sigma squared E, the individual level variance around the group means. So you can see that this is just a proportion. Yeah. This is the total variance, yeah, the EI, total variance, and this is the proportion of the group variance that is contributing to the total variance. So the VPC is equal to 0 if there is no group effects, or it will be equal to 1 if everything is due to the group effects. So the variance partition coefficient in this example will be much closer to 1 compared to this example, where the VPC will be closer to 0. Yeah. So visually, remember the group level variance is much more will be much smaller here compared to here, where the group level variance will be so the group level variance will be much larger here compared to here, where the group level variance will be smaller. So the interclass correlation, or the VPC, is it's a very nice statistic to calculate, because it's like a correlation coefficient, except it doesn't go negative. It's always between 0 and 1, and so it's useful to calculate that in a multi-level model, because it tells us what proportion of the total variation is due to level 2. It's due to our high level. So that gets us to the question of, well, is school an important level to consider when we're looking at exam test scores for students? Is neighborhood an important level for understanding the differences between people in terms of their health? So calculating the VPC is very, very useful. So I think in one of the previous analysis, we can calculate, say the group level variance is 0.169, the individual level variance is 0.848. So the VPC is just this very simple calculation, which is 16.6%. So we would say that 16.6% of the variation in student exam scores is due to variation between schools. So it looks like there's quite a significant, not statistically significant, but quite an interesting amount of variation in students' test scores that is due to variation between schools. It looks like schools matter for exam test scores. Yeah, this is just a figure to show how you calculate the residuals, which I think you're all familiar with. And this is a slightly technical slide about shrinkage factors. So it just reminds us that what we also need to consider this is the sample size at the group level, the NJ. So we want to discount the group level variance when the sample size of the group is very small. So because then if we're treating all groups, the same, so supposing we have 1,000 cases from Pearly, but just 2 cases from Q. Yeah. But we're treating the group level mean the same way as we treat group level mean of Q, the same way as we treat the group level mean of Pearly. That doesn't make sense because we have much more information about the group mean in Pearly compared to Q. So we want to discount the variance from Q and want to attribute more meaning to the variance from Pearly. So we use this shrinkage factor to sort of discount, to lower the weight of Q, the variance from Q, and increase the weight from Pearly. So that's what this shrinkage factor does. You don't have to worry about it because, of course, the software calculates that for you automatically. The other thing we get from multi-level models are caterpillar plots. So these caterpillar plots tells us how the residuals are distributed for each unit of our level 2, whether it's country or if our level 2 is schools or classes. So, and it ranks them from the lowest residual to the highest residual. So these caterpillar plots are a very useful visual tool for telling us whether or not we need a multi-level model. So if all of these residuals were distributed close to 0, then that means we don't need a multi-level model because really, no matter which level 2 unit you belong to, no matter which country you belong to, it really doesn't matter in terms of the residuals. But here we have a very strong evidence for the need of multi-level models because clearly for some countries, this is country over here, for some level 2 units, you have very low residuals, very low group level residuals. And for other countries, you have very high level group residuals. So this is saying that the group residuals the distribution of the group residuals are important. So they're not all distributed around 0. So this is another visual representation of the importance of a multi-level model. So it's similar. It does similar things to what a VPC, a variance partition coefficient, does. So the VPC gives you a number. The caterpillar plot gives you a visual representation of how important that number is. And then we can statistically test for whether we need a multi-level model or not. We fit a model without the group level variance and with the group level variance. And we compare the goodness of fit. We compare the deviance of the 2 models. So if the deviance significantly reduces, then we need a multi-level model because that improves the fit of the model. So this is what the comparison of the -2 log likelihoods of the model with and without the group level variance. So these are 3 ways of looking at the importance of the level 2. Do we really need a multi-level model? The variance partition coefficient. So if it's close to 0, maybe it's not important. The caterpillar plot. If all the group level residuals are distributed around 0, yeah, not significantly 0, you probably don't need a multi-level model. And then statistically, you can compare the deviance of the model with and without the group level residual. And if it's not significant, then you don't need one. So let's start analyzing a multi-level model, the very basic multi-level model. Again, we're using the Scottish exam test scores, and this time we have a few more variables. We have, apart from the case ID, the student case ID, we have the school ID. So schools are the level 2. Exam test scores are still our dependent variable. Cohort 90 is our explanatory variable, but we have a whole host of other variables like the sex, the social class, the school type. So whether it was independent is a private school, or whether it's a public or government school, and also whether the school was located in an urban rural area or whether the school was a religious school or a non-religious school. So these are characteristics of the school, so level 2, and these are characteristics of the individual student, which cohort they belong to, whether they were female or male, or which social class. So let's fire up R again. And this time, let's open up file 5.1R. .1 is this one. So 5.1R, double click on that. So it will open up the R script file, 5.1R over here. Let's read in the data file again. So read in my data. So call the data file, my data. And then let's do next steps. Yeah, so next step is we want to fit a basic multi-level model with no explanatory terms in there, just to decompose the overall variance into group and individual level of variance. But being R, it doesn't have all of these commands, these multi-level commands. You have to tell R to load the library containing all of these commands. But before loading the library, you have to install the package. So, those of you who are new to R, R is a little bit tricky sometimes. You have to know what package, which library your commands come from, and make sure they're installed and the library is in use. So this is saying use the library LME4. So LME4 is a specialist command code is specialized for fitting multi-level models. But before running that, we should actually install the package LME4. So before running library LME4, we have to install the package LME4. And this can take a little bit of time depending on how fast or slow your computer is. So it gives us a bunch of warnings, but it says it's managed to install it. And then we can use the library. So we have to run both of these, install the package LME4 and then run the library. So again, for those of you unfamiliar with R, just because the library is called a certain thing, it doesn't mean that the package has the same name. So we'll be using many R commands for which we'll need libraries, but sometimes you don't know which package, what is the package name? Install package what? So here, once again, Poe is your best friend. So Poe will tell you which package to install if you want to use a particular library. So that helps a lot. So we've installed the multi-level model. So now we're going to run the basic multi-level model. We're going to call it null model because there's nothing in it. There's no explanatory variables. And we're using LMER command. So this is different from the LM, the linear model command. LMER is for the multi-level model. So score is our dependent variable. And on the right-hand side, the other difference is that we now have 1 for the constant, and then this bar, and the school ID. So anything after the bar is telling R that this is level 2. This is the higher level. So this is saying that that we're sort of decomposing the error term. This is the error term over here into the intercept. and the group level residual. So the individual level residuals and the group level residuals. We don't need to tell R what the individual case ID variable is. It can do that by itself. It can construct it by itself. So just telling one and tells R that you want to create an individual level residual as well as a group level residual for school ID. And this is the data set. Yeah. So we can run this. So double click on that and run. And it's this new. So this is saying that this package didn't run properly. So let me just check. So I asked Poe, why did I get this error message? And it's saying maybe I didn't install and load the matrix package. So let me see what happens to the matrix if I copy these commands and put them in here. So I've now copied and pasted those suggestions from Poe saying install packages matrix, library matrix, run that. It's saying, do you want to restart R prior to install? So usually I say yes here. And it's doing something. So it's installing this matrix set. And now let's run the library LME4. And let's run the null model. Oh, still not. Can I check? Has anybody been able to run this okay? No, you're still getting this. That's weird. I just checked this on my computer before class started and it was working okay. Let me just check.
I just checked it. That is about the version of the matrix.
The version of
package. You can check the matrix package version.
Yes. Yes.
Select the package, the package there and check the matrix version. 1.6.
1.6 dot.
Yeah, because I just put there, it said that the matrix, if the version is less than 1.62, there are some source code on this.
Okay,
Yeah.
So thank you for that. Let's I'm going to step away from R from the moment. So I'll send a revised thing afterwards because it's slightly tricky to work out what's happening here on the spot. So apologies for that. But it's weird. I did run all of this on my computer before the class and it was working all fine. So it might be something to do with the way how this laptop is configured. So yeah, and how the matrix package is installed. So you have to trust my word for this, but if if we can run this LME or command fine, this is the kind of output that we get when we ask for a summary of the output. So now we have the intercept term like before, the average score for all the individuals in all the students, but we have now two residual terms. The group level residuals, so the residuals at the school level, as well as the individual level residuals around the group mean. So 61 and 258.36. So this is that decomposition of the overall residual into these component parts. The standard deviation. So this is another thing that people often mistakenly pay attention to. They say, oh my God, look, the standard deviation is really small compared to the estimate of the variance. So it's significant, but that's not the right thing to do. So often we do not use the standard deviation information because variances are not normally distributed. So really we should be ignoring this information, just concentrating on the variance, the estimate of the variance that we get. Yeah. So to calculate the variance partition coefficient is very simple. We just have to add up these two numbers. That's our denominator, and our numerator is the group level variance, 61. So the VPC is 0.19. Yeah, 61 divided by 319. So 19% of the variance in student scores can be attributed to differences between schools. The other thing that we can do is to do the compare the model fit, the deviance of the model with and without the group level variance. So here's the model without. So there's the linear model, the exam test score, just the intercepts. There's no explanatory term. Right? And we compare this model fit to that model fit of that variance components model. So we can compare the log likelihood of these two. So log likelihood of the null model of the multi-level model with just the two variances, and here's the log likelihood of the simple model. So we can compare these. This gives us the deviance. So comparing 2 times the log likelihoods, so it's a slightly tricky calculation, gives us a change of 370,3750 on 1 degree of freedom. It's very, very significant. So that's saying that, yes, we should be using a multi-level model because it significantly reduces the deviance. And the third thing that we can do is to look at the residuals. So in the R script file, when you got it all working, there's a whole set of commands that you can run to create that caterpillar plot. It's a little bit complicated, but once you create that caterpillar plot, you will get something that looks like this. This is telling us that there is a lot of difference between the schools in the residuals. Yeah, there's some schools that are much, much below the average residual, and some schools that are much higher than the average residuals. So this is telling you that, yes, definitely we need a multi-level model here, because it seems to be that schools are an important level for understanding exam test scores. So apologies, I won't go into each one of these, how we derive this in R, but it's there in the slides, and also more importantly, it's explained very well in the lemma material. So you can double click on these slides. Come directly from R5, R Practical 5, P5, and this will give you rather than the slides, it will give you a step-by-step way of understanding how we get why are we using each of these commands here. Yep. So, if this doesn't make sense, you can just go to the source file in the R practical 5. So sorry, let me get out of this one. Okay, so we've got the caterpillar plots, and then for the very last part, we'll come on to random intercept and random slope models. So far we've fitted a multi-level model, but it's not very interesting. There are no explanatory terms in it. So now what happens when we fit explanatory terms into a model? So this is the very basic multi-level model, but now we want to add in an explanatory term. So we want to put in an x variable over here to see what happens to that slope over here. So this is just a reminder that the total residual is just the sum of the group level residual and the individual level residual around the group mean. So what happens when we add in an x variable, an explanatory variable? Well, we're estimating the slope of that explanatory variable. Remember, so here the explanatory variable is at the individual level. How do we know? Because it has an ij subscript. We're estimating the slope of that ij subscript in this model, but nothing else changes. So, in terms of model complexity, it's just it's not making the model a lot more complex. It's just adding in one more explanatory factor here, which is the slope. We're trying to estimate the slope, the beta 1. But the UJs and EIJs remain exactly the same. So there's no additional complexity to the random part, the variance part. It's just the fixed part becomes a tiny bit more complicated because apart from the intercept, we now have this slope parameter, beta 1. Visually, how does it look? It looks pretty much like this. So our x variable is here. Our y variable, our y-axis is here. So instead of having a constant value for the mean, we're now estimating a slope parameter. So the effect of unit change in x on y. So this is the overall slope over here, and this is the slope for people living in Leeds, people living in York, people living in London. You'll notice that all of these lines are parallel. They're parallel because there's only one single slope being estimated here. So this beta 1 here is just one single parameter. So there's just one slope being estimated here. So it gives us, it's just one slope, exactly the same slope in each of these groups as the overall slope in the whole population. So the residual terms at the group level and the individual level residuals around the group mean exactly the same. So weight is a function of beta naught. So this overall slope is a function of beta naught plus beta naught is over here, plus beta 1 is the slope, the overall slope of age. So the group and individual level residuals mean exactly the same thing. So the UJs, the interpretation is the same. The beta 1 is also the same interpretation here. So that was an example where we've got x as a continuous variable, but our explanatory variables in linear regression models don't have to be continuous. They can be dichotomous. They can be categorical. So it will have exactly the same meaning. So it's, what is the mean of y when x is equal to 0 or when x is equal to 1 or 2, depending on which group it's in. So you can, of course, fit a multi-level model where our explanatory variable is continuous or categorical. That doesn't matter in terms of interpretation. In the R files, you can Again, we're still staying with the Scottish youth cohorts data set. And now we're fitting in more explanatory variables, so sex, social class, school type, and so on. Here, yeah, we've gone through what this data set looks like before, and you have to take my word for it that if we could run this in R, this is the model output. So here we're fitting a model, multi-level model, LMER. Our dependent variable score is a function of cohort 90. So we think that, cohort 90, which student cohort the student belongs to, has an effect on their exam test scores. And we're decomposing the overall variance into the individual and school level variances. And this is the data. So what is new? Nothing is new in the residuals. Residuals change a little bit, not very much. It was about 41 before for the school ID variance, about 219 for the individual level variance. So not very much change around the variance. But what is new here is that we have a new explanatory term in the fixed part of the model, cohort 90. So for every 1 unit increase in cohort 90, we're treating this as a continuous variable. We have an improvement in exam test scores of 1.24. Oh, sorry, 1.21. So this is a comparison of the random effects for the variance component model without the explanatory cohort variable and the random intercept model. So with the explanatory cohort model. So why is it called a random intercept? It's called a random intercept because we now have different intercepts for each group. Yeah? We have the overall intercept over here, but also we have a different intercept for each group. So this intercept is a random variable. That's what we're trying to estimate here. So before there was just a single single intercept, but now we're having estimating different intercepts depending on the group means. So it's called a random intercepts model in multi-level terms. So we can calculate, how the variance partition coefficient changed from the model with and without the explanatory term. So this is the model with cohort 90. This is the model without cohort 90. So if we did that, we would see that. I don't have that slide, but if we did that, we can calculate the VPC here and the VPC here. We can see that we'll see that the VPC has not changed that much. I can't do calculations in my head right now, but it hasn't changed that much. But and there's no particular rule about what will happen to the VPC when we add in level 1 explanatory terms to the model. But when we add in level 2 explanatory terms to the model, that's contextual variables. Say we had added in school type as an explanatory variable, that will always decrease the VPC. It will always decrease. Adding in a level 2 explanatory variable will always decrease the level 2 variance. So as a result of decreasing the level 2 variance, the VPC will reduce in size. So adding in a level 2 explanatory variable explains some of the overall variation in the Y variable at level 2. So from the R script, we can get this kind of random intercepts figure. Yeah, so it gives us some idea that the effect of cohort on exam test scores increases as cohort increases, but of course it's the same increase for every single school. So adding in a level 1 explanatory variable will always reduce the level 1 variance in the total variance, but adding a level 2 variance, the level 2 variance may stay the same, increase or decrease. And so for the final set of models that we'll look at today, we're looking at a random slopes model. So this is the variance components model with no explanatory terms. This is the random intercepts model with one explanatory term in there. And this is a random slopes model. So here you can see that the slopes or at the group level are no longer parallel. So apart from estimating a different intercept for each level 2 unit, we're also estimating a different slope for each level 2 unit. So here the variances at level 2 become much more complicated. So here's a decomposition. It's a further decomposition of the variances. So what's still the same? What's still the same are still the individual level variances around the group mean. Yeah. So this is group 2 over here. So we can imagine that there are all these spots, all these data points around group 2. So the EIJs remain exactly the same. Yeah, they're all individual level residuals around the group mean. The UJs remain the same. So these are the difference from the overall slope to the individual slope. Yeah. Sorry, the overall intercept to the individual intercept. So this is so the UJs remain the same. They're still about the difference between the overall intercept to the individual intercept. But what's different are these slopes. So there's the overall slope here represented by this beta 1 parameter. What we're now estimating is a difference between this slope and this slope. So for that, we calculate another residual, which is the slope residual. So this refers to the slope residuals, this U1J, U12 is the difference between the overall slope and this particular slope. Similarly, this U11 over here refers to the difference between the overall slope and this particular slope. Yeah. So this is the most complicated model that we'll be doing today. It's we've got 3 types of residuals. The individual level residuals around the group mean, that's easy to understand. The intercept residuals, that's also easy to understand. And the complicated one is the group level, the slope residuals. Yeah, the group level slope residuals. So the group level differences in the slope. So in terms of model parameters, we now have, apart from the individual level residuals, the EIJ, the group level residuals, we now have these U1Js, these group level slope residuals. So to make things easier, we say individual level residuals, group level residuals, and slope level residuals. So we're estimating 3 kinds of residuals in this complicated random slopes model. And as ever, it comes at a price. Price is more and more assumptions here. And the key one here is these group level residuals. They don't just follow a normal distribution. They follow a bivariate normal distribution. So, when you look at the normal distribution across 2 planes, the group U0Js and U1Js, they both follow a normal distribution. So, that it comes at a price with more assumptions being held on. And the other assumption here is, the other aspect to this is that we're getting a correlation between the x values and the U1Js. The x values and the slope residuals. Yeah. So this correlation is what is driving this pattern of lines that are fanning out or fanning in. So if the correlation between the random slope and random intercept, so here, let me show this visually. So this is the random intercept, and this is the random slope. This is the random intercept, this is the random slope. So we see here, there's a pattern where the lines, the group level lines are fanning out. And they're fanning out because there's a correlation between, a positive correlation between the group level intercept and the group level slope. Yeah. So if this is large and the group level slopes are positive, then the lines will be fanning out. But if the correlation between the group level residual and the group level slopes is negative, then the lines will be fanning in. So a positive value of this will be correlated with a negative value of this. So actually the lines will be, this line will be heading down this way. So this correlation between the intercept residuals and the slope residuals is another aspect, it's another complication of this model. So we have to estimate this correlation between the group and the group intercept and the group slope residuals, because this is what is driving the lines. This is one where the group intercept and the intercept slopes and the group intercept slopes and the group slope residuals are negative. And this is one where the correlation between the intercept slopes and the slope intercept residuals and the slope residuals is positive. So in R, it's always easy to fit these models, but then the tricky bit is in interpreting the models. So to fit the models, we have just one explanatory variable here, cohort 90. But in the residuals part, what is different is that we have this 1 plus cohort 90. So we're adding in a group level residual for cohort 90. And then at level 2, we still have the school level residuals. So this is telling R that we want to fit a random slope for cohort 90. And in the output, what is new? Well, for the fixed effects, that is the cohort 90 part, that remains pretty much the same. So nothing's changed there. But what has changed here is for the random effects. So now, apart from the intercept residuals at the group and the individual level residuals, so that is the same. What is new is this cohort 90 level residuals. These are the slope level residuals. So it's estimating a slope level residual plus the correlation between the intercept and slope residuals at the group level. So it's estimating two new parameters, the slope level residual, as well as the covariance, the correlation between the intercept and slope level residuals. So two new parameters and a whole bunch of assumptions being made about those parameters. So it's a much more complicated model, which comes at a price, but you might say, well, what's the point of all this complexity? So it's actually, this kind of model is very, very useful when we're doing analysis of growth charts, for example. So for those of you who work with in the medical field and you're interested in changes in height as babies grow, or changes in weight as babies grow, how do doctors know whether babies are growing appropriate for their height, for their age? They get those appropriate levels of height and weight for children's growth from these models. These will estimate, say we've got height or weight as a dependent variable and age as our explanatory variable. And the level one is the measurement occasions when we see these children being measured in terms of height and weight. And we have age as an explanatory variable, and age is also a random slope. So here we would have a random slope. Our explanatory variable will be age here, and we will be able to get the estimated effect of age, the predicted effect of age on height or weight for different groups of children. And we will be able to estimate, yeah, okay, there is this range of normal height and weight growth for a child, and they get those estimates from random slopes models. So they're extremely useful when we're looking at longitudinal data and when we've got repeated measures of the thing again, and we want to see to what extent they want to account for variability in the growth rates between different children. Yeah, so although it looks really complicated, and a lot of the time you'll say, well, I don't see the point of this extra complication because look, we're having to estimate intercept level residuals and slope level residuals, as well as the correlation between the two things, the intercept and slope level residuals at the group level. And we have to assume bivariate normal distribution and so on. So why bother? Well, it's precisely because of the uses in things like growth charts that they're extremely useful, because otherwise we wouldn't be able to say, yeah, what is a normal range of growth for a child of a particular age? So that is one of the key reasons for estimating these random slope models. And again, to test for whether or not a random slope is important, then it's very easy. We can compare the model fit for the model without the random slopes to the model with the random slopes, and to see whether there's a significant improvement in the fit of the model. And we can run an ANOVA test model to see whether there's a significant improvement in the fit of that. And this is from the R practical file. This is one where you can see here is the correlation between the intercept and slope residuals. What do you think? Do you think it's positive? Do you think it's negative? Are the lines fanning out or fanning in? Are they going more like that or more coming together? Well, okay, you've got these weird children. But apart from these three children, most of the children's lines, they're coming together. Yeah. So actually, so you're getting a lines fanning in situation. So the correlation between the intercept and slope residuals is negative on overall. So this is another visual representation. So another way of saying this is that there's much more variability in the students' exam test scores in 1984 than there is in 1994. Yeah, so the variability in exam test scores has reduced compared to earlier times. So this is also telling you that, yeah, there's actually something interesting going on here, that before, in 1984, students were doing these exams, but then, how they did, the schools didn't seem to make that much of a difference because so much variability. But now it looks like, 10 years later, it looks like there's much tighter clustering in exam test scores around the schools. So really, it looks like schools are really making a difference now compared to 10 years earlier. So again, this is another interpretation from a random slopes model that you wouldn't be able to get from a random intercepts model. So it's really telling us something about something has changed, and probably maybe schools are better at getting better at getting students to do exams, in 1994 compared to 1984. So it's really, again, if you're interested in group level effects, then this is interesting because it's saying, well, there's something really interesting happening at the group level that's changing over time. And the only way of estimating that is to do this very complicated random slopes model. Then there are some technical things about centering. So centering is important. So whenever we've got a random slope model, and our x variable should ideally be centered at 0, so the mean at 0. So it's very easy. You just subtract the mean from x there, and that will make a difference to the intercept residuals. It won't make a difference to the slope residuals. So technically, it is kind of important to center your in a random slope model. When you're estimating a different slope for x's, make sure your x is centered so that x equals 0 is meaningful. It's not at the baseline, but usually at the mean of x. So that's one thing to be wary of. So in the examples I've used so far, we've used a continuous variable. So here, age or time. So age is usually the metric of a growth curve model that the doctors use in their height and weight charts. But it doesn't have to be a continuous variable. We can also do a random slopes model for a binary or categorical explanatory variable. Of course, it's no longer a slope, but a coefficient, but it's exactly the same interpretation in terms of what this means for the variances. So you can use gender instead of cohort 90 as explanatory variable. Well, random slope, you can estimate a random coefficient of gender at the school level. So it would tell us something about how the differences between boys and girls differs between schools, by estimating a random coefficient for gender. And finally, we can add in some explanatory variables at the level 2. So what we haven't done so far are adding in explanatory variables at level 2. So this is, again, using the same data set. We've got explanatory variables at the student level, cohort 96, the social class of the student. And then what happens when we add in explanatory variables at level 2? So the difference here is the school type has a J subscript. So it's the same for every student within school J. So it doesn't have an IJ subscript, but all the individual level explanatory terms does. But in terms of the variances, there's no complicated difference in the variance. It remains exactly the same as before. So this is a model that fits these additional explanatory terms at school type. So here we've got school type, and we can use the same statistical significance test. So the t-test, divide the coefficient by the standard error. If it's greater than 1.96, it's significant at the 95% level, at the 5% level. So school type in this example is statistically significant. So it's saying that the type of school matters in terms of exam test scores, and so do all of these other explanatory terms. And in this particular example, the variance, the random part is, how complicated is the random part? It's got 1 plus cohort 90. So we're estimating a random slope for cohort 90 over here, as well as the covariance between the random slope and the random intercept at the group level. So it's a bit complicated model, but yeah, we can do that. And then you can do more complicated things where we're looking at interactions, but not just interactions between individual level variables, but interactions between a group level variable and an individual level characteristic. So, this is where, you get into really interesting questions about, does the effect of being a girl or boy differ between the type of school, or does the effect of being living in a deprived area depend on your individual level income? So, interactions here. So this is really looking at heterogeneity in these effects. Again, it's very simple to do that, to add in interaction terms. It really doesn't make any difference to the random part of the model, which is the most complicated part. But adding in explanatory terms is very easy and very simple to interpret once you know how to interpret interaction terms in a standard model. So remember, the complication here is in this part, not the EIJs. Most of the times we ignore the EIJs. It's in this part, the UJs, U0Js, U1Js. So this is the model without the random slope. This is the model with the random slope. So this is, as I said, the most complicated part. And it comes with a whole bunch of assumptions. So we're coming, I'm going to be here until 5 o'clock. So I'll, as I said, you've got all of the materials. You can work on them. I'm going to stay here. I'm going to try and work out why that model didn't work. Something to do with the matrix command. And I'll resend an updated materials to you sometime later this week. Yep. So yeah, thank you. Oh, before you go, please stay if you want to keep working on it, or please stay if you want to ask me questions. Come up to me, but before you go, can you please give me some feedback? Yeah. So you can follow this link or use the QR code. Please excuse my the fact that the model didn't work. As I said, I did try it before and it did work.